to. Thank you all for joining us today. We have Dr. Bastian Wibranek presenting today, who has joined the University of Texas at San Antonio recently as an assistant professor for digital design and fabrication at the School of Architecture and Planning. His research integrates design at the intersection of computational design methods, human-machine interactions, robotic manufacturing, and circular construction. He really takes an interdisciplinary approach where he's collaborating with structural engineers, computer scientists, engineers, material scientists, and roboticists. So today he is here to share with us some of the exciting research he's doing in this space. And he received his doctorate for his dissertation on design for reassembly from TU Darmstadt, Germany in 2021. And he has taught courses and conducted research on computational design and robotic fabrication at the Digital Design Unit and the Institute for Structural Design at Technical University of Braunschweig in Germany. He has published several articles and presented his work at international seminar and has given several keynotes. It's a pleasure to have Dr. Wibranek with us today. The floor is yours, Bastian.
Great, thank you. Yeah, just had some technical issues here. Let's hope the internet connection stays stable. So yeah, thank you very much, Diresha, for the invitation. I'm very excited for the opportunity to present my research. As you have already mentioned, I'm an architect, so there might be some different.
Oops, did we lose him? I think he's having internet.
Now I'm back. Sorry, it seems like the internet connection here at the downtown campus is not very stable at the moment.
Oh.
Did you, I got kicked out, right?
Right.
Yeah. Yeah, sorry for that. Technical issues, yeah. So let me see if it makes more sense to go onto a personal hotspot somehow from my phone. That seems. Can you still hear me? Internet connection.
Yeah, we can hear you. We can't see your screen yet, Bastian.
Okay, I have to share again, right? Okay, now it works again?
No, I can't see your screen yet. Yeah, I think, yes.
Now it was working? Okay.
Yeah.
Okay, now it works, yeah?
Right.
Okay. So yeah, let's jump back in. So as I said, yeah, I'm an architect from the Technical University of Darmstadt, where I was basically doing research and running courses for architectural students on how digital technologies like programming, robotics, additive manufacturing, like 3D printing, influence the design process of architects. As you can see in the center, I was hired basically to set up a robot lab, as I had former experience at the Technical University of Braunschweig, where I used some of these collaborative robots. And as you can see here, that's in the very beginning when they were very cleanly put into the lab space over there. But usually how it looked over there was this. So we are very intrinsic in these processes of materialization. So how do you bring things from the computer screen, things you design into the physical world, basically? And we do that by using computational processes in the computer, but also digital fabrication techniques. And today I want to talk with you about some challenges that I see and I hope to address with digital technologies and computational approaches. So 2020 was the year in which, according to estimates, for the first time, there were more man-made objects on this planet than biomass. You can imagine a complex crust of man-made objects is covering our planet. While nature's building materials are constantly changing their aggregate states, the largest man-made objects are poorly able to do so. This presents us with global challenges to which architects, as those at the very beginning of the value chain in construction industry, can make huge contributions. A building is usually reduced to a material graveyard at the end of its service life. The valuable building components and materials in buildings are lost at the end of the lifetime. So therefore, the goal must be to design and construct future buildings that can be deconstructed or reconstructed without significant degradation and loss of resources. As you can see here, one of the Frankfurt high-rises was demolished in 2014. And you can see that all the material components, all the energy that went into this building is basically degraded into dust. And although this is a spectacle many watch over there, it's devastating to our planet because a lot of energy went into the production of the concrete used for this building. Only to build a couple of years later, a very similar building with a very similar concrete structure at the very same place. And you can see that, there are a lot of issues when it comes to material consumption, but also energy consumption and labor efforts that go into these. This is more critical as construction industry, and I'm sorry, I just realized this is a German chart. But you can see the blue part, which basically is 53% of German waste production is basically construction waste. And if we can challenge that with our new technologies, that would be fantastic. At the same time, in architectural production and construction, we face the problem that the design part of construction or of architecture is already highly digitized. We use computer-aided design softwares, computer-aided engineering tools, and it's increasing when it comes to construction, but there's still a huge gap when it comes to digital construction techniques. And one of the projects that we did to approach the problem of this demolition waste was to see, what if we keep the process of demolishing and we figure out ways that we can use the data and the material in order to reuse even the demolition waste. So what we did here, we 3D scanned basically demolition waste, or in this case, concrete elements. And you can see it's very high resolution data. We can almost see the material on its granular state. And then we started to develop and design processes in which we can build with these 3D scanned stones, basically. So here you see different approaches to connectors between in this case, basic rubber material. And we did that with additive manufacturing, so 3D printing, in which basically the resolution of this fabrication technique fits very well to the highly and accurate meshes that we generated in the 3D scanning process. As you can see here on this image, it's almost a one-to-one translation from the digital data that was based on the physical stone into a connector in this case. We did a couple of experiments and then tried to, or I'm currently still trying to scale these processes. So we looked into scanning several stones and building more meaningful architectural figures, basically. As you can see here, the idea was to build a very basic arch in this case, in which it would be very important how these stones, the 3D scanned stones, would align to each other and orient to each other. Because you can imagine once they are, the interface between these stones becomes suboptimal according to the force translation between the stones. You want to avoid that. And that's where machine learning comes into play. We implemented a small algorithm, and that's a very initial stage of that. But where a genetic algorithm basically starts to search for the optimal orientation of these stones. And we basically optimize here towards an almost orthogonal orientation of the faces of the stones on the arch, on this arch curve, which is basically the thrust line for this arch. And you can imagine, obviously, you could do that manually, but it will take a lot of time and makes it very difficult to find the optimal solution. And then once that has been done, you can see again here, the dashed line is the thrust line. So that would be a line that only translates into thrust. So there's no tension needed in this kind of arch. And then you see this thrust line was basically calculated on the weights of the stones. And then we place these very simple or basic cubes along the thrust line as, again, connectors to build this thing. These were then 3D printed again, highly detailed elements, although the outer shell of these boxes is relatively simple, but you can see there's a lot of detail. And then there's the big question, how do you assemble that? And having never done something like that, we thought probably we were quite optimistic that this will be relatively easy, but it turned out quite fast that it's more challenging than we expected, because the orientation is very important and you have to find the right orientation while keeping the stones in place. And we figured out that it might be helpful to have a 3D augmentation of this assembly process. So we basically used an augmented reality headset here, Microsoft HoloLens, and augmented the assembly process with the exact orientation of the stones that we wanted to assemble. And here in the video, you see there's a lot of tolerances when it comes to the stones shifting. It was a bit better on the actual object. This is a little bit caused by the capturing process. And still, it was very helpful, because when you do that, you don't have to go back to a paper plan all the time, which is the usual process on construction sites at the moment. Instead, you would have a 3D model in front of your eyes that would allow you to understand which stone has to go in which orientation. And that drastically sped up the construction process or the assembly process of this little arch. And again, it's a small demonstrator, but it, so far, got a lot of attention, and people are quite excited about these ideas, because it shows a fully or almost fully digital design to assembly process based on a very analog or very unstructured material, in this case, the rubble material. And the detailing, yeah, can become quite impressive in these objects. Nevertheless, I mean, the biggest problem that I see with this, or I mean, a great achievement of that project, is that it could be an answer to use demolition waste. So the current process for taking down buildings is basically to demolish it. It's not deconstructed or anything. And even for modular buildings, as you can see here, this is a building constructed in Germany in the 70s, which was then just demolished 20 or 15 years later, although it was very modular, so it could have been deconstructed, so in a very sensitive way be disassembled. Still, it was just demolished. So you see these cranes would just use like a lot of force to bring these things down. So the previous project would be an answer to that. But at the same time, we started to challenge also the way we demolish or take down buildings. So we started to wonder if it would be possible to deconstruct a building, to cut it down basically in its initial components in such a way that you could already build a new building based on the components that you extract from an existing building. So therefore, you would again need to capture what is already available. And some people might argue that there exists a lot of information about buildings, but most of them, I mean, especially for old buildings, would only exist in paper plans. And yeah, even those plans are not accurate to the real as-built state of these buildings. So we went ahead and took our architectural building. You see the architectural building from the University of Darmstadt, where I conducted my PhD. And we basically used that as a case study for this approach. And you can see here, this is a video from Foster and Partners, one of the world's biggest architectural firms, which they're quite excited about this Spot Mini robot to capture basically the as-built status of their construction processes. They do that to monitor the actual building process, but we were more interested in using similar approaches for to see how we could deconstruct a building. We didn't have a Spot Mini, but we envisioned we would have one. So we still went and 3D scanned our whole building. So here you see a point cloud, a very dense point cloud of almost the entire building that was captured with stationary laser scanners. And then we started to analyze these buildings, this building, and see what kind of building elements are really there that we would like to use for a future building. So you can see we extracted from the overall building, we extracted the columns and beams, which are already prefabricated concrete components. Additionally, we did an exterior scan using drone photogrammetry to capture also the exterior of this building, to then, based on these relatively highly and very accurate data, to rebuild basically a digital model of the entire building, which we then again dispatched into the elements that would be available. So we focused here only on the concrete elements, slabs, facade elements, beams, and columns. And this would then become our building stock for a future building. So you can imagine this is, if it was a Lego set, this would be the Lego set for a new building from a building that is still standing. We then worked a little bit on basically a building catalog. And then the big challenge was, how do you actually extract these elements? It's concrete, it's not as easy as taking Lego buildings apart. And my former university, the Technical University of Braunschweig, they have a large facility that focuses on additive manufacturing. So you see a 3D printed column, but they also have machinery that allows to cut very accurately into concrete elements. And based on this cutting, you can see develop dry joint construction principles. So you can imagine they have a concrete part that is not very accurate in its connection details. And in order to make the more accurate connection details, they cut into the column. And what is so beautiful about this process is that it not only helps us to deconstruct or cut the building into parts, but we could do that already with a new joining idea in mind. As you can see here, a dry joint that would automatically shift the different parts into the right position. And then we, again, I said, I have a very I try to connect research and teaching as much as possible. So we started to look into this kind of ideas with our students. And one challenge that we found with the idea of deconstruction buildings might be the storage of building components between the actual deconstruction process and the construction of a new building. And here our students basically came up with the idea to store the building elements that were extracted from the previous building in a bus station. So they would build a bus station, which anyway has fairly good access to the transportation network, and then the building components could be stored over there. And they started to develop further ideas about how we could develop actually connection details that would allow us to assemble parts back from these components. And here you can see a lot of iterations, thinking about the process, how it could be extracted from the site and could be delivered basically to new sites from the bus stop. All these in this kind of very diagrammatic approach, but always keeping in mind that these elements for the future building, we wouldn't want to make a solid building, but instead rely on interlocking principles, dry joining principles, which you see here, in this case inspired from Japanese wood joining, which you can, with a little bit of effort, transfer also into concrete assembly methods. During this construction process, you would obviously have to consider various processes to assess the quality of the concrete parts, maybe repair concrete parts, which this project here was investigating, almost like a hospital for concrete parts before they go out into new construction projects. And then, basically design tasks. So in this case here, a bridging structure. And again, the question would have been, how can we translate how can we extract the right parts from the existing buildings in order to build this bridge, or even to make use of all the components that could be available to build even several structures from a building that is not needed anymore. And with our students, we looked into, again, dry joining methods, which would allow us to avoid complicated joining details that would make it, again, hard for future generations to take these buildings apart. So we developed a computational process that would allow us to design, again, a bridging structure purely on compression forces. So we could simplify the connection details. And in this case, it would almost stand without any connection details. So the little black details that you saw here, these are mainly to avoid buckling or sliding of the structural members of the bridge. They are not really translating too much force, because the entire structure is, as I said, compression only. And then we started again to look more as a sketch or a small scale demonstration, how to do that robotically, as we didn't have access all the time to this big tables, to this big saw that you saw in Braunschweig. But we basically sketched the process and cut here wooden parts again, which would reflect the dimensions of the concrete parts. And then, yeah, you can see one attempt to assemble these parts. And then finally, all the cut elements, again, on a model scale. Yeah, that's a typical method of architects, to use models, small scale models to build these things. And then the final assembled thing, which again is completely assembled without glues. Only the shoes that sit on the plate to basically ground the whole structure are fixed using screws. Everything else is just purely dry joint. Again, almost like a complex Lego system. And this project, yeah, allowed us to basically reconsider the idea of deconstruction of buildings, which currently is only done in order to save components from becoming waste, and they might have been stored somewhere else. But this project really pushed the idea to do deconstruction already with the construction of a new building in mind. And while this project again allows us to rethink how we deconstruct, and also gives us an idea about how we could actually construct in the future, we also started to consider ideas how we actually envision how we should design and build our future buildings. So we looked into robotic assembly methods, and you can see here these are becoming relatively complex Lego bricks in this case, that have to, basically were designed for the robot to be placed, but also to be disassembled fairly easy. So you see these zigzag shaped elements that have a little bit the purpose of dealing or negotiating the robotic capabilities, because at the very beginning of this project, our robot didn't have any sensing skills, and that can cause some problems in construction, because not everything is as precise or as ideal as you wish. So we basically sketched a project, again, a small demonstration of the idea of how could we use these building elements in order to make buildings, almost like editable throughout their lifetime. And you see here, it's a small scale installation. But what was happening, the robot would constantly pick these zigzag shaped, in this case, foam blocks, and constantly replace them in an art installation that would further change the meaning of this installation. So you see these bright sprinkles on the installation. That's there were some hidden messages on the installation that would be reassembled, changing the meaning of the whole structure. You can see here, if I don't know if you noticed, there was the word act that would be changed into the word react once the robot replaces these elements. And that's again a placeholder for the idea that the function of this building can change, the usability, the program of the overall building. And basically to show that if we wanted to achieve that, there were ways how we could design for future buildings to be basically editable. Again, this is highly involved with developing computational processes for the design of these structures. So you can see here we had a volumetric shell structure that then has to be analyzed computationally to basically find the right combinatorial arrangement of these parts. As you can see, it's different sizes of these zigzag shapes. Some are more are long in the one direction, then there are shorter elements, and these allow us to basically build various structures. You can see here another small scale demonstration to show that even with this, we are able to build cantilevering or arching structures that are then again, able to be completely disassembled. And we started to look into create gradients of material properties. You can imagine all these foam blocks, they have the same weight. And what you see here, we started to add these gray blocks, which are heavier than the red blocks, which would allow us to build even more cantilevering structures, which is something quite important in architectural construction. You can see here again the robotic assembly process. And again, this doesn't have any sensing skills here. This robot, it just executes a plan that is pre-computed for it. But this would be a way to showcase that we could even build bridges. But it also shows how delicate the calculation was in this case. So we really pushed it to the maximum of this. So once you remove or add weight at the wrong place, it would completely collapse. Which raises also some of the questions. How much do we actually trust our computational processes in cases like that, where the combinatorial space of these elements can become very big, basically. We also started to look into different modules, different geometries of these parts. Here also some experiments that a colleague of mine, Andrea Rossi, at this time at the Technical University of Darmstadt was doing, that again deal with other geometries that would also allow to build cantilevering structures, but always designed with the purpose to be assembled by a robot, to basically automate the robotic assembly process. Because if we want to become more granular in our built environment, while keeping the editability of these parts, it makes sense to think about automating these things instead of asking humans to do the labor of these. Again, all these projects are usually or were usually done with architecture students. Here and there were some computer scientists involved that helped us setting up certain things. But it's also a great opportunity always to allow architects to interface with these high technological tools like robotics, which we do not see on too many construction sites yet. But we have to train architects in these things to bring them to the construction site. Yet there are a lot of challenges in building with robotics. I mentioned that these don't have any sensing skills, so they would just execute our plans. And you see here, they drop parts, they don't even notice until a human would interfere with these. They don't see their errors basically, unless you implement something to do that. And at the same time, even if they would sense that they did something that was not intended, they wouldn't know how to adjust to it. So if we want to go to real construction sites, we would have to adapt these things. And that's where we started to reach out to the computer science department, basically, the autonomous systems labs at the Technical University of Darmstadt, which they use reinforcement learning to attempt these kind of problems, to allow machines to adapt to certain problems. As you can see here, the robot would understand that it caused an error and would learn how to adapt its path in order to do that. Before we reached out to them, they did a lot of great experiments. Like here you can see learning by demonstration, in which a PhD student is basically training this robot arm to play table tennis. So the student is showing the robot some basic strokes to return the ball that is captured by a camera system. And then again, there are probably many hours there are many hours going into the training process and programming of these things. But after a few training sessions, this robot, not a few, but many training sessions, this robot learned a policy that would actually allow to beat a PhD student of computer science in a party of table tennis. And we reached out to them not only because of their skills in training and teaching robots to use basically machine intelligence, but also because they are they do research in tactile sensing for robots. As you can see here, the robot would adapt its grasp based on the object that you hand over without destroying objects. And while these sensors here that you see on the fingertips of these robot hands are quite expensive, we started to look into sensors that would be more affordable and would also allow us, would enable us to have higher dimensional features, basically. As you can see here, this is a vision-based tactile sensor. So it's basically a camera that has a soft film in front of it with these black dots embedded in this basically silicon skin. And these blobs can be detected by a blob detection algorithm, and then yeah, we can basically, or we were able to calculate the force that is being applied once something is grasped. And you can imagine this also allows, here you see how the sensor is basically built. It's a $20 camera, a few 3D printed parts, and this silicon film that actually, this is the hardest part to fabricate to keep it transparent. But it allows for several modalities. Yeah, as I said, you can still see elements through it. Here you see this orange element because it's a transparent sensor. It would allow us to detect forces, but also rotation of elements. And then we started to do some first experiments here, handover tasks that are basically just triggered by applying force on the fingertip of the robot, but also object inspection on the right top. So it would understand, there's the object, and would slide along this object to find the center point of this object for it to be grasped. On the bottom left, you see we were also thinking about that these could be human-robot collaborative processes in which the robot would basically sense the direction for a building element to be pulled to. And again, it's on model scale, but that's a basic method of architects to work in. And then on the bottom, you see it, in this case, almost autonomous placement of these elements by a robot. Obviously, this would again allow us to reconsider what kind of elements we start to assemble, and we started looking into these blocks here, which from a first look they might just look at like very simple blocks being placed on top of each other, but these are actually SL blocks. This is a relatively complex Lego block again that allows for interlocking mechanisms, and it's based on research by Xi, a mathematician involved in architectural design projects. So yeah, you can basically imagine it's an L block and an S block that are fixed to each other in this kind of configuration. And then with this configuration, you are able to find engagements that would always allow these parts to really immobilize each other. So these elements don't move anymore once there are 4 or more parts being placed. So we don't need any glue, but still we can build cantilevering structures, and these would only be sequentially assembled. And here you can see such an assembly process. So you see they can become relatively complex. And again, the beauty of these processes is you would only be able to remove them in one direction, these blocks, which allows for more complex assemblies. Here, for instance, in column, it is nice. These blocks can be scaled from very small, like 1 centimeter scale, up to very big scales. and basically the bounding box of these elements can be articulated differently in different materials. So it could be wooden elements, concrete elements, or more articulated elements that are 3D printed. Yeah, here's another one. But for me, the beauty in these blocks is really the possibility to assemble and disassemble them without harming the elements. So you wouldn't need to screw, to drill, use any adhesives like glue, and still would be able to, without demolishing anything, to take these things apart. What is more challenging when you consider these kind of blocks is how do you actually find their arrangement, their assembly, and how do you find arrangements in aggregations of these blocks that are relatively big. We developed an algorithm that would help us doing that, where we basically inscribe the different engagement with these letters. So you see here we type strings that are then translated into these different geometrical transformation. And you can play a little bit with these, but it would always be an architect having to figure out these kind of different string combinations, basically. And that again brought us back to our colleagues of the computer science department, which they are experts in reinforcement learning. And we started to formulate this problem of finding the right orientation into a reinforcement learning problem. So here in the bottom now you see basically what architects would like to do is to draw a curve that then would be populated or would be sequentially assembled from these blocks. So we started to implement a reinforcement learning algorithm with its objective function, so basically reward function, in which the agent would always try to keep the blocks as close as possible to the curve, while trying to avoid collisions of blocks that would prevent the curve from further growing. And then, based on this reward function, we were able to implement this algorithm, which, I mean, for me as an architect is very beautiful, because it seems to me, or it looks to me, like these blocks are now finding their position. It's not really, I tell them, I don't have to assign where they have to go, but rather the blocks, their intrinsic values find these blocks. We started to test different algorithms. So again, we tried to see if we can use evolutionary algorithms, which didn't perform very well. We tested reinforcement learning algorithms, but also a greedy algorithm that would really that is hard coded and would really just perform this one task. And again, the greedy algorithm, which is hard-coded, might perform a little bit better, as you can see in this comparison, where we basically, the red parts are very far from being optimal or being along this curve that you see on the bottom, and the lighter parts being very close to optimal. But what we learned, or what I believe is one of the advantages in this reinforcement learning algorithm, is that it can really adapt its objective somehow, its objective function. So you see here, for instance, as soon as we started adding obstacles to this course, the greedy algorithm, we would probably have to go back to the code and really adjust the code in order to find a more optimal solution that would not deviate so much from the curve. As you can see on the top, on the left side, the greedy algorithm starts to go around the obstacles from basically outside, whereas the reinforcement learning algorithm, because it also has a longer horizon of where it wants to end and wants to go, it achieved way better results in that. And then again, you can, with these elements, it's beautiful. You can stack these curves into wall elements. We started to really explore the different combinatorial. And here in these, you see, there's the grid of blocks, but then only these black elements in the that you see here would be the ones that I have to take out, almost like a nail. Yeah? If I take out this block-like nail, only then I can start to remove the other members of these blocks. Here you can see columns with the same approach. Again, walls, slabs. All of these can be made from these reversible building blocks. And then obviously you can also start to create combinations of different elements. So you can have more foundation elements, and then members that would be more having bridging properties, and you can start really explore very complex arrangements and combinatorics of these elements. And again, then the big challenge would be, how do you actually assemble these things? You see a human, and I can tell you, it's even for a human, it's not too much fun. I mean, especially if I give you a very precise plan of what I want to achieve, the combinatorial aspect of figuring out this is the orientation, I have to put it here. That's actually, beside being a tactile task, very complex already. So we started looking into how we can actually automate these with our robot, while also making use of the tactile scale, because these elements have to slide in very precisely. So there's not a lot of room for tolerances or, as soon as the robot grabs the part a little bit suboptimal, or the part has some tolerances, it would basically collide without any sensing. So we started to improve this sensor that you saw earlier. So this one is here called GearSight, which is based on research from MIT, and a big company is also working behind that, which I'm thinking not allowed to share yet. Anyway, so this is again a jail, and behind it there's a camera, and you can see here the camera image. So we don't have dots anymore, but instead we have these different light diodes in there that allow us to understand the three-dimensional deformation of this gear. And it almost has like a fingerprint, which serves here as the dots from the previous sensor. Again, this sensor, material-wise, you can build that for $50. You just need the PCB board and the materials. Assembly and fabrication of that is a little bit more expensive because it's labor-intensive, because a lot of things are not mass fabricated yet, but they are affordable. And then, we started basically looking into how could we train a robot to assemble these things. And here you see we did that basically by demonstration again. We didn't do that by guiding the robot, but instead playing Tetris on the keyboard to assemble these, and then recorded the signals from both from the finger sensor, from the tactile sensor, but also the position of the elements, as you can see here with these Aruko markers. And then finally we were able to do very simple basic assemblies. And then we kept on training the robot based on curriculum learning, which is basically you tell the robot where it has to go, this path would work, and then you start adding little errors, little deviation of the optimal path, so it would constantly adapt basically on this. Unfortunately, during my PhD, we didn't manage to build a bigger structure. This would be one of the goals. The research project is still they even got funding, I think a quarter million, to investigate this. Again, it's basic research. It's basically looking into the idea how we have to design building elements, building components in order to, both with robot skills in mind, but also with this idea of taking these parts apart. So my biggest vision for these kind of elements, and I'm not saying that the SL blocks are the final solution to change our construction industry, but for me they are a placeholder for this vision of buildable build environment that we can edit, that it's easy to take apart again, and that we can even maybe in the future even change while we are inhibiting these kind of buildings without creating dust, noise, and all other harms on humans and also on our environment. Again, as I mentioned, it was a collaboration. Back then I was still a part of the digital design unit at the Technical University of Darmstadt, which is the architecture department, and the Intelligent Autonomous System group led by Dr. Jan Peters. And yeah, so to conclude, I hope I was able to show you some projects that dealt with the manipulation of our built environment. This could start from demolition waste or from the idea of using deconstruction methods that inform how we can build in the future, but also combinatorial ways that we can use for our future buildings that would be aligned with automation in construction, mainly through robotics. And yeah, now my hope is that I got you a little bit excited about the challenges that we have in architecture, and in particular in designing things for the future. I'm very open to collaborations, and I'm still in search of a PhD student. So if you know someone who's interested a little bit in design, but also in the hard programming that goes into all these projects, I would love to get in touch with you. So thank you very much, and yeah, I'm ready for your questions.
Great presentation, Bastian. Very different from what we are typically used to. Great visuals and very interesting applications of the both the robotic space as well as some of the algorithms, the reinforcement learning algorithms.
Thank you.
Questions, folks? You can either ask or post a question in the chat window.
I do have one question.
Mm-hmm.
Hello, hi. That was a great talk, Dr. Wibranek. I did have one regarding when you're using the demolished debris to create these things like arches and stuff like that. Your simulation is like created this photo scanned version of the mesh, but that would use the geometric center of gravity, whereas the center of gravity of these blocks would depend on the homogeneous nature of the debris, and debris can consist of cement and rebar and other things. How do you account for that change in geometric center when you're simulating the balance?
Yeah, good question, good point. I'm wondering, no one ever raised that question so far when it comes to the center of mass for these blocks. Yeah, you're right. For the simulation of this arch, we basically assumed that it's a homogeneous material, that it would not have any hollow parts or rebar that might change the center of mass. I'm wondering if there would be geometrical ways or measurement ways to figure out where the actual center of mass of things are. Because I mean, on the one hand, there are techniques how you could almost like, what is it, like X-ray these blocks to see if there's a rebar inside. Right. And that's being done for reuse of concrete parts. So there are tools that you can. It's again basically a scanning process where you would start to understand if where there are metal parts inside. It's not super precise. It would be precise enough probably for the tolerances. We have to add a lot of security measures into these kind of processes if you really wanted to build with these processes. I don't know. I mean, and again, to see if it's hollow. Yeah, you probably can also measure that somehow, but it will never be probably super precise. What I started to look into with my students now is to really augment these pieces of debris. So to add parts onto the, so basically you just have this block in the center, and then you would add almost like Lego-like features to the blocks itself that would cover the whole thing. So with this, you could develop also assembly strategies that could also adapt to structures that would not only work with compression forces, for instance. But yeah, I believe one could, and I know that again, my former university, they started a research project on this idea of reusing, not demolition waste, but basically the project with a deconstruction where you would cut the building, and they are looking into scanning and assessing basically the non-visible properties of these concrete structures or concrete components. But thanks for the question. Yeah, great.
Thank you so much. That was really exciting. Yeah, looking forward to it.
Other questions? You've shown some results on the DQN and RL and the greedy algorithms. Can you go to that slide, Bastian?
Mm-hmm.
It was really interesting to see that a hand-coded greedy algorithm performed better
Mm-hmm.
hard-coded, right?
Yeah. Let's see. Yeah. So yeah. So I mean, yeah, the greedy algorithm, I mean, basically what it does, it always would really, it would just check, and it's a bit to go, but I think it would only check the next, where to place the next block, basically. And it would always try to be as close as possible on the curve, which works in most cases. And you see that the DQN and the PPO algorithm, in some cases, they outperform the greedy algorithm a little bit because they have this horizon. They learned basically a little bit of horizon, which we implemented there. So it would understand that check the or get a reward also for how you would perform 5 blocks from now, whereas the greedy algorithm really just looks at the proximity of the center of this block and tries to bring it as close as possible to the curve.
Right. Yeah, it would be good to see what would be the, I think you have a wide range of curves in here. It would be good to see what would be the optimal space for RL. What structures work well in the RL scenario. I think that's interesting. And the other question I had was, do you have the test beds here set up yet? The robotic test beds or any of that?
In my lab?
Yeah.
No, not yet. I'm very excited to have met Jianan Kai, professor from construction science, who has similar to the robots that we used here, this universal robots, a little bit smaller. Hers is a UR5, which is a payload of 5 kilos. But it's a mobile robot, which is really exciting for me because it allows me, or it would allow us to build bigger structures. And yeah, things take a little bit longer here. I don't know if that's also caused a little bit due to the pandemic situation, but we try basically to join our lab spaces, our robotic lab spaces, to do research, and that didn't go as fast as I was hoping. But there will be in the future, hopefully within the next few, I would say month, there will be a robotic setup exploring these ideas further here at the downtown campus in the architecture faculty. And
there'll be a lot of interest, I think, in trying to realize some of the new AI algorithms that are being developed and see how well they perform in some of the test beds. I think there's a lot of opportunity for collaboration.
Yeah,
Really
yeah,
exciting.
definitely. I mean, what was for me very exciting about this collaboration with the computer science department is, or what I believe is challenging currently for, I mean, especially for architects, because we're like if you look at the curriculum, how architects are trained at the moment, this part of explaining program languages or understanding algorithms, how they work, what is a reward function, is not really at the core of what we would teach architectural students. So I would also, I mean, from my education, I didn't have any knowledge about machine learning. Yeah, that came in my PhD, and I'm very excited about these ideas, because there's a huge space of opportunities in the domain of architecture to apply all sorts of machine learning algorithms. In this case now it was more probably combinatorial aspects, but then also robotic programming. But there are so many other things like space layouts and optimizing structural capacities of elements. And it's such a pity that it's so much work to get to a certain to an understanding of vocabulary between the different disciplines. If we don't start teaching architects and designers the language, but then also obviously it has to also be a little bit in the other direction. But I still think that it's our duty as architects and designers to go one step into the direction of computer science and develop at least the skills to communicate. What kind of reward function would you want to have? Yeah, what is a reward function? What is it actually you're trying to achieve with these algorithms? So I would be also very exciting if one could figure out ways to collaborate on these kind of ideas. To obviously you need to break down the concepts a little bit, because architects, it's not their core curriculum, but I sense also they are very excited about these opportunities.
Absolutely. So yeah, there will be quite a bit, I think, of opportunity coming up in the future. We are also launching a master's in AI.
Great.
Also, there'll be a lot of those students who might be interested in these kind of applications. So thank you so much for taking time and presenting your research to us. This is very inspiring, what you're doing, and what we typically are not used to seeing in our ECE realm also. So I think it's just like expanding our understanding of how these algorithms can be used in different spaces. Thank you.
Thank you very much for the invitation and the questions. It was a pleasure. Thank you.
Bye.
Bye-bye.
See you all.